Hello students, welcome to Interconnecting Physics. Today in this video I will teach you electric current density, temperature coefficient of resistivity and superconductors. So without wasting time, let's get started. For regular updates you can follow me on given links. Current density. It is defined as the amount of current per unit area of the conductor held perpendicular to the flow of the charge. Means the cross-sectional area of the conductor is always perpendicular to the flow of the charge. It is denoted by capital J, which is equal to I divided by A. So J can be written as I divided by A, and please note that current density is a vector quantity. We know that current is a scalar quantity, but current density is a vector quantity whose magnitude is given by this equation. This equation I divided by A, this gives the magnitude and the direction is same as that of conventional current. Okay, what is conventional current? In last video I have told you, again we will repeat it. Suppose we have a conductor and a voltage is set up across the ends of the conductor through a battery. Let us say this potential is V. Now this end is positive, this end is negative, and electric field setup is capital E vector, which is from positive to negative. Now free electrons inside the conductor starts moving from negative end to positive end, and the direction of current is opposite to the motion of electrons. That is, the direction of current is always in the direction of electric field, that is from positive end to negative end. This is known as conventional current. So J, the direction of J is same as that of conventional current. If I is along this direction, then J will also be in this direction, that is in the direction of electric field. Now SI unit of current density is ampere meter inverse square, because current is measured in ampere, and the SI unit of area is meter square, and it will be ampere meter inverse square. Now dimension formula will be written as M0 L minus 2 T0 and A. This is the dimension formula for current density. Now current density can be written like this. Suppose if we have Di current, small electric current passing through an element of surface area dA, then we can write Di equal to J dot dA. That is for small current, small area element. Now if we want to calculate total current through the total surface area, then we integrate this equation, and the integration of Di will be I, which is equal to integration of J dot dA vector. So I can be written as J dot dA, means I current can be written as in the form of current density and area element dA vector. Now we know that dot product of two vectors is always a scalar. Now a current density is a vector quantity, area vector is a vector quantity, and the dot product of two vectors gives us scalars. That's why current is a scalar quantity. Now current density can be written in terms of drift velocity. We know J equal to I divided by A. And what is the relation between current and drift velocity, which is NEA VD. If you want to know this relation, then click on the I button, you will get this relation. Now I equal to NEA VD, when we put this value here, A cancels out with A and the J will become NEVD. So this is the required relation between current density and the drift velocity. Now in general, for a charge Q drifting with velocity V, if any charge, if we are not talking about electron, we are talking about any charge, maybe positive, maybe negative, and that charge is moving with velocity V, then current density can be written as NQV vector. This Q is any charge and this is the drift velocity of the charge. Now Q is positive or Q is negative, J always will be in the direction of electric field. Always remember this point. Q may be negative or positive, but the direction of J is always in the direction of electric field. Now let us do some numerical so that we can understand the concept of current density. Okay, so find the current density in a wire of diameter 0.2 centimeter in which current of 10 ampere flows. I have already told you, while solving numerical problems, always write down what is given to you. So given diameter of the wire is 0.2 centimeter, and in SI unit it will be 0.2 into 10 raised to power minus 2 meter, because 1 centimeter is 10 raised to power minus 2 meter. Now current is 10 ampere. Okay. Now let us calculate the current density. We know the formula, current density is I divided by area. Okay. Now I is given, but area of the wire will be pi r square, because diameter of the wire is 0.2 centimeter. And what is diameter? What is the relation between radius and diameter? Radius is always diameter divided by 2. So what will be the current, what will be the area? IA equal to pi d square divided by 4. So substitute this value here, we will get J equal to I divided by pi d square multiplied by 4. So current density will be 4I divided by pi d square. 4 is 4, I is given as 10 ampere, pi is 3.14 and d is 0.2 into 10 raised to power minus 2 meter. And when we calculate this, we get J is equal to 3.18 into 10 raised to power 6, and the units of current density in SI ampere meter inverse square. So hope you are clear with current density. Now microscopic form of Ohm's law, or we can say vector form of Ohm's law. For this, let us consider we have a conductor of length AB equal to L. Now let us say this conductor is connected with some battery having voltage or potential difference V. And we know the relation between electric field and potential. Electric field is always negative of the potential gradient. Okay. So if we take magnitude of this equation, we will get E equal to dV upon dr. If here in this situation we have dV equal to V and dr equal to L, then we will get E equal to V divided by L. So here we are with E equal to V divided by L. Now we know that simple form of Ohm's law is V equal to IR. Now we know that R equal to rho L over A, where L is the length of the conductor, A is the area of cross section of the conductor, and rho is the resistivity of the conductor. Now V can be written as, if we put the value of R here, then V will be I rho L over A. Now I divided by A, this will become J rho L. Now if we substitute V equal to EL, okay, if we cross multiply it, we will get V equal to EL. So EL will be equal to J rho L. L cancels out with L, and E will be J rho. So in vector form we can write E vector equal to rho into J vector. So this is the microscopic form of Ohm's law. In simple form, V equal to IR. Okay. So here we are replaced with electric field, I is replaced with current density, and R replaced with resistivity. Further, if sigma is the conductivity of the conductor, then we know that sigma is 1 divided by rho. Then we will get E equal to J divided by sigma, and J vector will be sigma into E vector. So this equation can be written like this. This equation can be written like this: E equal to J rho or J equal to sigma into E vector. Both are the microscopic forms of Ohm's law. Now, derivation of Ohm's law using concept of drift velocity. Now, we will derive Ohm's law using concept of drift velocity. This is very important. For this, let us consider again a conductor having length L, and this is connected with some battery having potential difference V. Okay. Now, electric field is set up whose direction will be from positive to negative. Now, E equal to V upon L. We know E equal to V upon L. Now, electric current in a conductor is given by, we know the relation between current and drift velocity, I equal to NEAVD. And what is VD? It is the drift velocity, which is equal to small e, capital E, tau divided by m, where E is the charge on the electron, capital E is the electric field, tau is the relaxation time, and m is the mass of the electron. So when we put the value of Vd here, we will get n E square A tau divided by m multiplied by V into L. Now I divided by V. If we divide this equation with V, we will get n E square A tau divided by ml. Now we know that V equal to IR. Okay. V upon I will be R. So write this equation as V divided by I. We will get right hand side ml divided by n E square A divided by tau. Now from Ohm's law, we know that V divided by I equal to R. Okay. Now this equation and this equation. When we compare these two equations, then we see left hand sides of these equations are same. So right hand side should be same. So R will be equal to ml divided by ne square A into tau. Now mass of the electron is constant, length of the conductor is constant, number of electrons per unit volume is constant, charge on the electron is constant, area of cross section of the conductor is constant, relaxation time is constant. That means all the terms in the right hand side of this equation is constant, and we can say that R is a constant, and hence we have derived Ohm's law, because this right hand side, all terms in the right hand sides are constant, so this will be a constant, and we know according to Ohm's law V over I is always a constant. So we have derived Ohm's law using concept of drift velocity. Okay. Now factors on which resistivity and conductivity depends. Now we have derived Ohm's law here, and what we got here, R equal to ml divided by ne square A into tau. This is very important relation which shows how resistance depends upon the multiple factors of the conductor. So R equal to ml ne square tau into A. If we separate L into A, we know that R equal to rho L over A. If we compare this equation with this equation, we will get rho equal to m over ne square tau. Rho equal to m ne square, m divided by ne square tau. Now resistivity depends upon number one, number of electrons per unit volume, and number two, relaxation time. So first of all, we will discuss dependence of resistivity on number of electrons per unit volume. Since number of electrons for every conductor is different, number of electrons per unit volume is different for different materials. I have told you in last video that for copper, number of electron is 10 raised to power 26 per unit volume. It means for copper it is 10 raised to power 26 per unit volume. For another material it will be different. So that means resistivity depends upon the nature of the material of the conductor. So indirectly, basically resistivity depends upon the number of electrons per unit volume, and number of electrons per unit volume for every material is different. So we can say that resistivity of conductor depends upon the nature of the material of the conductor. Now number two, the relaxation time. Now what is the relaxation time? It is the time between the two successive collisions. Now we know that, let us consider a conductor. Some battery is connected across the ends of the conductor having potential differences V. This is positive, this is negative. Now, when electron starts moving from negative end to positive end, what will happen? It gets drifted with drift velocity Vd equal to E, capital E tau divided by m. It gets drifted and strikes with the ions of the conductor. And will be at rest. Again it gets drifted, get accelerated and strikes with the ions of the conductor and becomes at rest. Again it gets drifted, strikes with the ions of the conductor and will be at rest. Again it gets drifted, strikes with the ions of the conductor and becomes at rest. So that means, what is relaxation time? Relaxation time is the time between the two successive collisions. This is collision between the electron and ion. This is the collision between the electron and ion, and this is the time where there is no collision. Here electron is relaxing. electron is taking rest. There is no collision between the two successive collisions. So this is called as relaxation time, and the distance travelled between two relaxation time by the electron is called free path. Okay. Now what will happen when temperature increases? When temperature increases, what will happen? The relaxation time will decrease. Why? Because more collisions will be occur if temperature will be increased. If temperature will be increased, then there will be more collisions. That means relaxation time will be decreased. Okay. So that means relaxation time tau is inversely proportional to temperature. If temperature increases, relaxation time will be decreased. So that means, what is rho? Rho is m over n e square tau. Rho is inversely proportional to tau, okay, and tau is inversely proportional to temperature. That means if temperature increases, tau decreases. If tau decreases, resistivity increases. That means resistivity is directly proportional to temperature. Means if temperature increases, resistivity increases. Means if temperature increases, resistivity increases. According to this relation, if temperature increases, relaxation time will decrease. If relaxation time will decrease, the resistivity will increase. That means if temperature increases, resistivity increases. And we know that when temperature increases, there will be more and more collisions between the electron and ions. There will be more opposition in the flow of the current. That means, what is opposition? Opposition is the resistance. That means if temperature increases, resistivity of the conductor will be increased. If temperature decreases, resistivity of the conductor will be decreased. Now, dependence of conductivity on temperature. We already studied if temperature increases. If temperature increases, resistivity increases, and conductivity is inversely proportional to resistivity. That means conductivity will be decreased. If temperature increases, resistivity increases and conductivity decreases. That means conductivity is inversely proportional to temperature of the conductor. Okay. So this was the dependence of resistivity on number of electrons per unit volume, that is the nature of the material, and the relaxation time. Now let us see further limitations of Ohm's law. Number 1. Ohm's law is not applicable in unilateral networks. Unilateral network means that networks which allow current to flow in only one direction. For example, in semiconductor devices, that is diodes, transistors, in these devices, Ohm's law does not work. Number 2. Ohm's law is not applicable for non-linear devices. What is non-linear device? In which the graph between V and I is not like this. The graph between V over I is like this. And this happens for semiconductor devices. Semiconductor devices. Okay. So that means Ohm's law is not applicable for non-linear devices. Non-linear elements are those which do not have current directly proportional to the applied voltage. That means for such elements, there will be change for different values of the value and current. Means graph will be like this. It will not be a straight line. It will be some curved line between the voltage and current. So for this, Ohm's law does not valid. Examples of non-linear devices are thyristor, electric arc, semiconductor devices, etc. Now applications of Ohm's law. There are so many applications of Ohm's law in daily life, but we are lack of time, so we can discuss only few of them. So fan regulator is one of the very common device where current flowing through the fan is regulated by controlling the resistance of regulator circuit. You know, in summers when we use fans, then what we will do? If we want to increase the speed of the fan, what we will do? We regulate the fan through a regulator. That means when we use regulator, we basically control resistance. We basically control resistance. So when resistance increases, current I decreases and the speed of the fan will become slow. When resistance decreases, current increases and the speed of the fan become more. So that means through regulator we can control the current through which fan speed can be controlled. And there are so many examples of, there are so many applications of Ohm's law like Kirchhoff's law, Norton's law, Thevenin's law. These all laws are based upon the Ohm's law, and in this chapter we will discuss Kirchhoff's law later on. Now, ohmic and non-ohmic devices. The main difference between non-ohmic and ohmic devices are they obey Ohm's law or not. Ohmic devices are those devices which obey Ohm's law and there is linear relationship between current and voltage applied. Okay, there will be linear relationship between voltage and current like this. And non-ohmic devices are those which do not obey Ohm's law, that is they don't have the linear relationship between current and voltage, they have like this relationship like this. And mainly semiconductor devices don't obey Ohm's law. So these are non-ohmic devices. So how does resistivity depend upon the temperature? We already discussed resistivity depends upon the temperature. When temperature increases, resistivity increases. But we don't know the exact relationship between the resistivity and the temperature. So in this topic, we will come to know the exact relationship between the resistivity and temperature, and we will discuss how does resistivity depend upon the temperature. We already know as the temperature of the conductor increases, thermal agitation increases. Thermal agitation means thermal speed at room temperature will be increased. There will be more and more collisions between the electrons and between the electrons and ions. That means average time between the two successive collisions decreases. Therefore, conductivity decreases and resistivity increases as the temperature increases. For small temperature variations, we can write rho equal to rho naught 1 plus alpha T minus T naught. So this is the relation through which we can know how resistivity depends upon the temperature. Now, this rho, resistivity at temperature time T, this rho naught, resistivity at temperature T naught, and we basically take T naught as 0 degree Celsius. Okay, and this is alpha. Alpha is called as temperature coefficient of the resistivity and is constant for a given material. Alpha only depends upon the temperature and that to only small extent. Now, temperature coefficient of resistivity can be written as, if we rearrange this equation and multiply it and divide, we will get alpha rho minus rho naught divided by rho naught into T minus T naught. This is the temperature coefficient of the resistivity, and this can be written as delta rho divided by rho naught into delta T. What is delta rho? It is the change in the resistivity, that is rho minus rho naught. What is rho naught? It is the resistivity at temperature T naught, and what is delta T? It is the change in temperature, that is T minus T naught. This rho naught is also called as original resistivity. So, temperature coefficient of resistivity is defined as the change in resistivity per unit original resistivity per unit change in temperature. Okay. So again, I repeat, alpha is defined as the change in resistivity per unit original resistivity per unit change in temperature, and the SI unit of alpha is Kelvin inverse or degree Celsius inverse. Why? Because the SI unit of delta rho will be ohm meter. SI unit of original resistivity will also be ohm meter. This ohm meter cancels out with ohm meter and we are only left with the SI unit of temperature, that is Kelvin, and when we take this Kelvin in numerator, that SI unit will become Kelvin inverse, or we can write degree Celsius inverse. Now, we know that resistance of conductor depends upon its length. We know that R is directly proportional to length and R is inversely proportional to area of the cross section of the conductor. We know that resistance depends upon the length and area of cross section, but resistivity does not depend upon the length and area of cross section of the conductor. In last video, we have discussed this. Okay. Now, As the temperature changes, the length and area of cross section of the metal also change. Obviously, if suppose we have some metal, when we heat this metal, length will be changed, area will be changed. So that means when as the temperature increases, the length and area of the metal also increases. But these changes are quite small and the factor L over A may be treated as constant. Okay, please note this point because these changes are small and this factor L over A can be treated as constant. So that means that R is rho L over A. If this is constant, then we can say that R is directly proportional to rho. So, this equation rho equal to rho naught 1 plus alpha T minus T naught can be written for resistance, that is R equal to R naught 1 plus alpha T minus T naught. Okay. Now, the materials with resistivity of the order of 10 raised to power minus 8 ohm meter. The materials having resistivity is of the order of 10 raised to power minus 8 ohm meter. These materials can be treated as good conductor of electricity. And the materials which have resistivity 7.5 into 10 raised to power 17, 10 raised to power plus 17 ohm meter, these materials are considered as insulators, and the materials having resistivity much smaller than insulators and larger than conductors are treated as semiconductors. Semiconductors we will discuss later on. Now for conductors, temperature coefficient of resistivity is always positive. And for semiconductors, temperature coefficient of resistivity is always negative. Always remember this point. For conductors, alpha is always positive, and for semiconductors, alpha is always negative. But for insulators, temperature coefficient of resistivity is negative but very low. Now, why manganese and constantan are used in making standard resistance coils? This is very important questions because when we talk about some standard resistance coil, we use only two materials, manganese and constantan. Since the value of temperature coefficient of resistance is very small for alloys like manganese and constantan. Okay, because for these two materials, the temperature coefficient of resistance, that is alpha, is very small. That means very small means the resistance does not change with change in temperature. Okay, if alpha is very small, what does that mean? That means the resistance of the material is not changing with the temperature. That is why manganese and constantan are used in making standard resistance coils, because while doing the experiment, when temperature is increased or decreased naturally, then these variations in temperature does not make any effect upon the resistance of these two materials, that is manganese and constantan. That is why these two materials are used to make the standard resistance coils. Now let us do some numericals so that concept of temperature coefficient of resistivity or resistance can be cleared to some more extent. So numerical number first, at 27 degrees Celsius, the resistance of resistor is 83 ohm. What is the temperature of the resistor if the resistance is found to be 100 ohm and the temperature coefficient of the material is 1.7 into 10 to the power minus 4 degrees Celsius inverse. Now, let us write what we are given with. Given resistance of the resistance at 27 degrees Celsius is 83 ohm. That is R27 means resistance of the resistor at 27 degree centigrade is 83 ohm, and resistance of the resistor at theta temperature, which we have to measure. Theta we have to measure. So R theta equal to 100 ohm and alpha we are given with 1.7 to 10 raised to the power minus 4 degrees Celsius inverse. Now we know the relation R equal to R naught 1 plus alpha delta theta. What is delta theta? It is T minus T naught. Okay. So R27, this equation for 27 degrees Celsius can be written as R27 equal to R naught 1 plus what is delta theta? T27, and but we take T naught always 0. Generally we take T naught as 0. So delta theta will be 27. So we can write R naught 1 plus 27 alpha. And for theta, r theta equal to r naught 1 plus alpha theta, because theta minus 0 will be theta. Okay. Now let us divide these two equations. R theta divided by r27, r naught 1 plus alpha theta, r naught 1 plus 27 alpha. R naught cancels out with r naught and result is 1 over alpha theta 1 plus 27 alpha. Now let us put the value of r theta, which is 100 ohm. Put the value of r27, which is 83. Now let us cross multiply this and put the value of alpha. We will get the value of theta is 1241 degree Celsius. Okay. So in this way we can calculate the temperature of the resistor if we are not given with. Okay. Now numerical number 2. A conductor rail has cross section 15 centimeter square. We are given with A, which is 15 centimeter square, which is equal to 15 into 10 raised to power minus 4 meter square. Resistivity is given as 7.6 into 10 raised to power minus 8 ohm meter at 0 degree Celsius. If the coefficient of resistance of the material is 0.005 degree Celsius inverse, we are given with alpha, which is 0.005 degree Celsius inverse. Then calculate its resistance per kilometer when temperature is 50 degree Celsius. Means we are given with temperature which is 50 degree Celsius and we have to calculate the resistance R50. Okay. Now we are given with A, rho, alpha, T and we have to calculate R50. So let us calculate this type of question. Now first we are given with R50. How we will write R50? R50 will be equal to R naught 1 plus alpha delta theta. So first of all we have to calculate R naught. So what is R naught? It will be rho L over A. What is rho? 7.6 into 10 raised to power minus 8 ohm meter. What is L? Per kilometer. What is L? 1 kilometer. 1 kilometer means 1000 meter. Okay. So when we put 1000 meter divided by area given 15 into 10 raised to power minus 4 meter square and we will get the value of R naught 0.05 ohm. Now let us calculate R50, which is R naught 1 plus alpha delta theta. Okay. R naught is 0.05, 1. What is alpha? 0.005. What is delta theta? It is 50, because what is delta theta? It is T minus T naught. T is given 50 and T naught we generally take 0 degree and here is also given 0 degree Celsius. So the result will be R50 is 0.063 ohm. So in this way we can calculate the resistance. Next type of numerical is a metallic wire has resistance 1.1 ohm at 20 degrees Celsius. That means R20 we are given with 1.1 ohm and resistance 1.7 ohm at 100 degrees Celsius. Okay, 100 equal to 1.7 ohm. Find the temperature coefficient of the resistance of the metal. We have to calculate alpha. Now how will we write R20? R20 will be R naught 1 plus alpha delta theta. Okay. And how will we write R100? It will be R naught 1 plus alpha delta theta. Okay. Now let us divide this. R20 divided by R100. This cancels out with this 1 plus alpha. What is delta theta for 20? It is 20. Okay. Multiplied by 20. What is delta theta for 100? It is alpha into 100. Okay. Now let us cross multiply it. What is R20? It is 1.1 ohm. What is R100? It is 1.7. So when we cross multiply, divide and multiply, we will get alpha will be equal to 7.9 into 10 raised to power minus 3 degrees Celsius inverse. Okay. So in this way we can calculate the different values. In first numerical we calculated the temperature. Okay. In second numerical we calculated the resistance. In third numerical we calculated the temperature coefficient of the resistance. It means any of the question if you are asked with, you can calculate in very easy and very simple manner. We have learnt all the three types of numericals for calculating temperature, for calculating resistance and for calculating temperature coefficient of the resistance. Okay. Now what is thermistor? It is very important topic and in 12th examinations, it can be asked for 2 marks. Okay. So a thermistor is a resistance thermometer. Now this thermistor is made up of two words. Thermistor, thermistor. Therm means temperature and istor means resistor. So it means it is the resistor whose resistance depends upon the temperature. Okay, so a thermistor is a resistance thermometer and it is a resistor whose resistance dependent upon the temperature. Thermistors are usually prepared from oxides of various metals such as nickel, iron, cobalt, copper, etc. Means it is also an alloy. A thermistor is usually enclosed in a capsule with epoxy surface. It comes like these shapes. Capsule, it can be in the form of capsules like this and like this. Thermistors are used as temperature sensors and they can be used in everyday like fire alarms, ovens and refrigerators. So that means your 2 marks question is complete. What is thermistor? How is it made up of? How does it look like? What are its uses? So your 2 marks question is complete. Now what are superconductors? Even superconductors in 12th class physics is not so vast topic, but for 2 marks or 3 marks question you may be asked in your examination. So what are superconductors? Okay, there are certain materials for which resistivity suddenly becomes zero. We already studied when temperature increases, resistivity increases. Okay, it means if temperature decreases, resistivity decreases. That means there is some possibility if temperature becomes very low. That means at that stage resistivity can be made up to zero. So it means there are some materials for which resistivity suddenly becomes zero below a certain temperature, and this certain temperature is called critical temperature, and the material in this state is called superconductor. Above this critical temperature, the resistivity follows the normal behavior of the metal, and it was discovered by H. Camerlin Owens for mercury. He saw for mercury at 4.2 Kelvin temperature, the resistance suddenly becomes zero. Suddenly becomes zero. You see here, here is the resistance, but at 4.2 Kelvin temperature, it suddenly becomes zero. It means below this temperature it is zero, resistance is zero, but above this temperature resistance increases with increase in temperature. That is why this line is saying with above this critical temperature the resistivity follows the normal behavior of the metal, that is above critical temperature if temperature increases resistance or resistivity increases. But for critical temperature, that is 4.2 Kelvin, which is very low for mercury, the resistivity becomes zero. So it is clear from the graph that resistance of mercury drops abruptly to zero below 4.2 Kelvin. If an electric current is set up in superconducting material, it can persist for long time without any decrease. That means if any electric current is set up in any superconducting material, because there is no loss, there is no resistance, there is no loss, so that current will persist for a long time without any decrease. And what are the uses of superconductors? Superconductors are used to construct very strong magnets. Number two, they have very wide applications in material science and high energy physics. They are used to make ultra fast high speed computers, and they can be used for transmission of high electric power over long distances, because there is no loss of power in the superconductors because there is no resistance. If there is no resistance, current can be persist for long time. That means these superconductors can be used for high electric power transmission for long and long distances. So this was all about superconductors, thermistors, temperature coefficient of resistance, numerical regarding that, current density, limitations of Ohm's law, applications of Ohm's law, etc. So this was all about today's video. Thank you very much. If you want PDF notes, you can ask me in comment section or you can follow me on my Telegram channel. Don't forget to like, share and subscribe. Stay happy, stay healthy.